have not taken that far away. Never, ever. Which I don't blame them. My son loves Charlestown. I imagine that that's also part of why he got in trouble, because he loves that place and was very excited. Yeah.
Trying to get like a job there, because I had everything to do with my first major. So.
Yeah.
Also, my advisor for biology is Dr. Mildred.
Yes.
He's the vet there. So.
Yeah. I really, really like Charlestown Landing as well. And so my son has a lot of know-it-all attitude. So there could have been some of that, because he's an expert on Charlestown Landing. Yeah, so he's probably trying to show off a little, yelling at Damon to slow down so he could tell him about the ship or whatever.
What young kid isn't an expert on Charlestown?
Y'all, I got to be honest with you. I know that you're like, yeah, we know. I'm so ready to. I'm being recorded. So. But boy, it's been a time. But we are near the end in here, and I don't think we're going to write another proof until we're reviewing for the finals. So we're just going to draw some pictures and do some counting, and it'll be fun. Yeah, me too. I'm really bad at pictures, but that's all right. I'm even worse at programming them, which is why one of your homework questions is like, draw your own. I can't figure this out. I tried for so long to make a thing, and I was like, no, it's just not happening. We're just going to be done with it. They can do it. So y'all will get that honor. Okay, so we are talking about now in chapter 12, formal languages and regular expressions. This is going to go into 12.2, where we're going to talk about machines, steady state machines, a finite state automata. Yeah, we're doing computer science now. So we're going to talk through languages, and these, like, every language has a defined set of rules, and that those rules are syntactical. I don't know. They're syntax rules. So this is good for programming language stuff, as well as just language in general. So in English, like, there are certain rules and definitions. A sentence in English is a string of words. But not every string of words is a sentence, right? So not every string of words would be accepted in the English language as a sentence. Not every string in a language is accepted as a correct code, right? And not every sentence is grammatically correct. Not every string of words is in language. The word is a string of letters, but not every string of letters is a word, right? So there are levels of this thing happening. So not every string of letters is in the language. This was really funny when my son was learning how to read. He would be like, what does H, K, L, 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 M, M, N, T spell? It's like, well, just because you said a bunch of letters doesn't mean it spells a word. And there are rules, and you got to have some vowels. And he's like, okay, K, O, 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 O. Can we stop? So computer languages are similar, that certain strings are legitimate words and a compiler will do things with them that it's supposed to. Other things will be rejected by whatever the program is. When I'm doing stuff, which is what I was doing, trying to write your homework assignment and trying to draw one of these machines, and there were a bunch of red things in my code and it didn't spit out a PDF. And also the pages you just tore out of your stuff, which you've now thrown away, also didn't have the pictures. It just had the code that was supposed to make a picture, right? Because I was missing something. And so these things, there are rules involved here, and like how a thing recognizes something. Like in my stuff, I had to call a package so that it would actually make the picture, and I hadn't called a package. I had just used the package. And so I needed a use package skis, so that it would make the bubble diagrams for you. Seems real silly, but anyway, so computer languages are like that when you that there are an infinite for loop or whatever. Like there are things that can go wrong, and you have to know how to make what you're trying to say work in the language that you're given. So we're going to do this in sort of like a really baby way, but obviously you would use it in more, you would flush this out in other areas, other classes. So we're going to have an alphabet that we're working over. So like thinking the analogous thing here for computer science people, probably like a binary would be fine, just using zeros and ones. Or mathematicians, let's just go ahead and we'll think about the English alphabet. And so you have this finite set of characters, so 26 in the English alphabet that you're using. A string over sigma, that big sigma is the alphabet. The string over sigma is a sequence of elements of sigma, or the null string, or the empty string, which is epsilon. The length of a string is the number of characters in the string. The null string has length 0. And the formal language is the strings that are accepted. So the set of strings over the alphabet is a set of strings over the alphabet that fit a certain criterion. I don't know. So we're going to practice with this. And it's weird and it's uncomfortable at first, but we'll get used to it, I hope. And for some of you, it may not be. But so for all of these examples, 1 through, I don't know, whatever number we're on here, we're 5. We're going to use this alphabet. Oh, well, let me turn that line off. Or our alphabet is just A, B. So the first example, we're going to do the language L1 that consists of all strings that begin with an A and have at most 3 characters. So the L1, this thing will be all of the strings that are accepted in this language. So L1 is going to be a set of strings of A's and B's. Give me a string that would be accepted in this language. A, B. Just A would. A, B would. A, B. A, B, B. A, B, A. A. B, no, because it needs to begin with an A. What about just a 2, just A? Let's see, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Cool. Good. Length at most 3 characters, so that's it. We've done it. Alrighty. Next up, we are going to do L2. This is going to be palindromes. Palindromes are the same forward as they are backwards. We're going to just list 6. This would be a much bigger language. Like A, B. Those work. A, B, A. A. ABBA. That's faith integration. Check. Huh? Well, like Abba Father. Or ABBA. Yes, faith integration, the band. Pretty sure they're not. AA would work, yes. I love that. Okay. That's great. We were supposed to list 6. Good job. Okay, sigma to the n is a set of all strings with length n. So we're going to make a set of the strings of length 4. It's still the same alphabet. A and B is our alphabet. And we're going to make all of the strings that have length 4. Anybody got a guess about how many there should be? Good.
I was gonna go one higher, but
At least 2. Good. There's 16. Why?
it's 2 to the 4.
Yeah, we should learn counting first, but yes, there are 2 things here, 2 things here, 2 things here, 2 things here. So 2 to the 4th is 16. All right, ready? I'm going to do columns of 4 columns of 4 things. Ready, steady, go. Thank you. A. A, B. A, B, A. A, B, A. B, A. No, this one doesn't have any restrictions on how it starts. You're good. B, A, B. This is a real computer scientist doing this in a methodical way. Keep going. B, A, B, A. I would just start listing random crap. What? B, B, A, A. Okay. B, B, A, B. B, A, B, B. B, 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 B. How about A, B, B, B? And B, 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 A? B, 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 A? Okay. We did. B, 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 B. Oh, yeah, we just sure did. Thanks, y'all. How about B, A, A? Nope, that's up there.
I think it's A, B, A, B.
A, oh, yeah. A, B, A, B. What about B, A? Oh, B, A, B, A is there.
And then A, B, B, A.
A, B, B, A. A, B, B. Good? All right. Okay. Next up, we're looking at sigma plus. This is a set of all strings that have length at least 1. So this is going to be all strings except the empty string or the null string. Sigma star is a set of all strings over sigma. So this is sigma star is actually equal to sigma plus union with the empty string or the null string. Which also means that sigma plus is sigma star toss the empty string. Okay, so now we're going to talk about some like operations on the language. And then we'll do operations on the strings in a minute inside of the language. So I always use like thinking about like a Spanish and English dictionary here as like our languages. Our accepted languages would be the words that are accepted in those languages. But like, so we have an English dictionary and a Spanish dictionary, right? So that's our L and our L prime. The concatenation of L and L prime basically just think about putting those books in one book next to each other. So you would be looking at the strings inside of here would look like XY, where X is in L and Y is in L prime. That you can have like hi and agua next to each other. I don't know. I didn't go with Olaf because I didn't want you to think it had to be the same. It's just pick any word from either language and smack them next to each other. The union of L1 and L2 would be any word that would be in the dictionaries combined, right? So it's any string that is either sitting in that X is in L or X is in L prime, that X is an English word or X is a Spanish word. I hurt myself somehow with my Apple Pencil. I stabbed my hand with it. I don't know what happened, but it's hurting. I'm at that age where I just randomly hurt myself. Like I stepped on my own foot while playing soccer with my son this week, and it still hurts. Bad. Okay, this word, this person is, I believe, the first computer scientist. I don't know if that's true. His name is, I think, George Claney. He says his name is Claney. His son says it's Clean, or Cleany. But he is like, no, my name is Claney. But the Claney closure of a language is the set of the concatenation of all strings in L. So this is pretty weird, and on the language like level, this on the element level is easier to understand. But so this is this set of all concatenations of strings in L. So take any strings in L, smack them next to each other. The set of all possibilities to do that would be the Claney closure, which is a lot of things, right? If we're talking about the English dictionary, right? Let's talk about the English dictionary, any word in there next to any other word in there, which means any two words in there next to any third word in it, like this blows up pretty quick. Cool, huh?
Yeah.
All right. So we have these three like sort of action things, and we'll look at these on the element basis as well in just a few minutes. So we are going to do this. So we're going to do this on the like language level with an example before we look at the regular expressions or regexes or whatever you guys call them in computer science. Okay, so L1 is a set of all strings consisting of an even number of A's. That's that's a big language because it's just even numbers. So like none, 2, 4, 6, 8, 10, 12, so on forever. Okay, so L2 is B, 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 comma, B, B, comma, B, B, B. We good? Okay. We are going to find the concatenation of L1 and L2. So what the elements in there look like. So L1 is like the null string A, 1, 2, 3, 4, 5, 6. Okay. So what do these things look like in L1 concatenated with L2? Yeah, it could be. So we first, when we concatenate with the empty string, though, we can get B, BB, and BBB. So we'll get those three first. And then, yes, what you said. So you're looking at A, B, 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 B. So that's the twos. And then the four A's. So B. B. Oof. B, B. And then you would keep going with the six. So every element in L1, smack next to every element in L2, forever, so on. Okay. L1 unioned with L2. So this is the set of strings in either language. The empty string. B, 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 A, 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 A. Any string from either language, just write them all down. So the Clady closure of the union would be the concatenation of any of these elements. So we can make things like BAA. We can make things like BAAB. We can make things like B B B B B B B B B B B B B B B B B. Because we could just put a bunch of B's next to each other, right? We can make A B A. Yes. Yes. What kinds of strings could you get? Describe it in words. Strings of A's and B's where what is true? What would be the only, could you have A, B, A, B? Why? Single A's are a problem, right? So any string of A's and B's where the blocks of A's are even numbers of A's. Any string that fits that you could get.
So like A, B, you can do that one.
B. No. But you could do B. Yeah. Okay, regular expressions in the alphabet sigma. Our regular expressions are going to be the null string. Also, any of the elements in the alphabet. Elements. There's a lot of elements in the alphabet. So if it's like, A's and B's, A and B would both be regular expressions as well. So if R and S are regular expressions over sigma, our alphabet, then so are R, S. This is the concatenation of R and S. Which again just means put them next to each other. This, the bar is a or. So this is a choice. This is R or S. You get to choose. R star is the concatenation of R with itself. Any finite number of times. Including no times, which is weird. So for example, these would be things like the empty string R, 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 any finite number of times. Okay, so element wise, we're going to practice what this looks like. So we have this alphabet A, B, C. We're trying to sort of figure out what's going on here with this A bar, B bar, C star, bar, A, B star. I'm not sure why I don't leave you space to do this, but what kinds of strings would be in here? What does this language, what does this describe? Give me a string that would be in this this language described by this regular expression. A, okay. What else? A, B. Not AC. So the or, once you make that choice, you're stuck in there. So if you choose here, only one A. If you choose here, you can concatenate B or C. Okay. Good. I say BC is fine. You choose B, and then you're going to star, so you get to choose again. You choose C that time. Mm-hmm. So the choice is inside the star, so you can do that. Good. Yeah. Yes. What if we choose over here? What do those look like? Yeah, copies of AB. So AB, AB, AB.
Not BA.
No. Is that okay? So this describes just a singular A. This is any string of A's and of B's and C's, not A's. No, this is any string of B's and C's because the concatenation thing you can choose, concatenate, choose, whatever. Yes. And then this one is copies of A, B in pairs. A finite number of copies of A, B in pairs, including none. So the null string's in here too. Okay. Any questions or comments about that example? Emily, you had your hand up, but we have established it or answered it, or no? Did you not have it?
I was probably stretching.
It was like here. It's not a good stretch.
I don't know what I was thinking.
You're getting ready to make an espresso.
I wish they would let me on bar.
They don't?
I'm trained on it at a different restaurant, and then I applied with my whole application being strictly about how I can run bar. And they're like, that's a shift lead thing. You have to be here for a couple months before you can. I was like, really? My whole application was about it.
Did they schedule you for that day before those finals?
You know, it's funny, this week, I was supposed to go in for work on Wednesday, and then I looked at the schedule Wednesday morning, and I'm not scheduled, even though I was the night before, and so I texted my manager, and I was like, what happened? And she was like, oh, I just felt like giving you a day off. What about my day off for?
Right. Could you give me the day off that I asked for?
Yeah. I don't know, what days are you in?
That Wednesday, I think, right?
Okay, they haven't released that schedule yet.
Okay.
But I know the week before I'm scheduled on that. Whatever.
Okay. The language defined by regular expression are the language. Oh, I forgot the empty set up here. The base could also be the empty set. I'm going to be real super honest. I don't really understand if that's just that the alphabet is empty. Yeah, what's the difference between the empty set and the null string?
Null kind of represents not existing at all.
Uh-huh.
And that there's empty, which just is empty.
Exists but is empty.
Yeah.
Okay. Well, this makes me feel like this is the opposite of what you just said, but I don't know if this is true. I mean, I don't know if it is actually the opposite of what you said. The language of the empty set is the empty set. The language of the null string is the set containing the null string. Yeah, that is what you said. And then the language of A, the regular expression there would just be A itself. This stuff is pretty weird. That the concatenation of R prime inside of the language, you can do that like on the language level, put them next to each other. You can do the same thing with the choice. The choice is a union. That makes sense. The star thing you can do once you've already done the thing too. All of those are like rules, definitions, whatever, but let's actually try to use it and see what we can do, okay? So we are going to use set notation to find the language defined by the regular expression, and then we're also going to describe this thing in words. So the regular expression here is A or B star. So we're first going to give like a set of what things would be in this language, and then we're going to describe what those things look like. Our alphabet is A, B. We are looking at A or B star. So what would the things in here be? What does that star mean? Any combination between the A's and the B's, yes. The star on the outside there is concatenate A or B with itself any finite number of times. If it was just A's or just B's, it would be like this. Right, so that it's an order of operations thing. That star being on the outside of the parentheses means you can choose, concatenate, choose, concatenate, choose, concatenate. This means, you choose once and then you concatenate. Okay, so being on the outside, you get to choose that however many times you want. So this is the empty string, including no times. So the empty string, we can choose A, we can choose B, we can choose A, B, we can choose ABA, we can choose BB, we can choose BA, we can choose BA, BBAB, whatever. Okay, so in words, how would we just, oh, Eunice, there's a lot of things on your desk. um, pages 21, 22, 23, and 24 need to be replaced in your packet. So tear out those and put those into your packet. And there's the stapler. Well, I wouldn't say that since there's mistakes in your note packet, but whatever. Prepared when it matters. 20, it's those 4 pages. I don't know. Tear them out of your note packet.
Oh,
They're in order. It's 4 pages in order. Okay. In words, how do you describe this language? A string of A's and B's, all strings of A's and B's, right? Including the empty string or the null string. Okay. Any questions or comments about that? We're not to that page yet. We're on page 19. Okay. Ooh, huh. How about this one? We have 0 star, 1 star, or 1 star, 0 star. Choose first, left or right side. And then you can do concatenations. Yes, but they have to stay zeros followed by ones on the if you choose the left, and ones followed by zeros if you choose the right. Yeah?
Yes.
So we could choose like a bunch of zeros. Say we've chosen one or the left hand side, whatever. We can choose a bunch of zeros and then some ones. We can choose some ones. We can choose some ones followed by some zeros. We can choose 0, 1. We can choose 1, 0. I can't choose 1, 0, 1. Does that make sense? I can't choose 1, 0, 1 because that's not allowed here. Yeah?
Just 0 or just 1?
Just 0, just 1, fine. The null string's fine. Okay. How would you describe that in words? I'm going to say all strings of zeros followed by ones. Because it could be a bunch of them, not just a 0 and a 1. Or a string of ones followed by a string of zeros. So if you choose the left, you've got a string of zeros followed by a string of ones. If you choose the right-hand side, you've got a string of ones followed by a string of zeros. The bar is an or. The star is a concatenation, which means just like put them next to each other. Mm-hmm. Yes. All right. On number 3, our alphabet is zeros and ones again. And we have the regular expression 0 and then 0 or 1 star.
So this is just binary starting with 0, right?
Yes. I'm not going to say that. All strings of zeros and ones that starts with a, whoa. With a 0. So you see that you have the 0 to begin with, and then you can do 0 or 1 star. So that's any combination of zeros and ones. Okay, so give me some things that are in there.
0, 0, 1, 0.
Is the empty string in there or the null string? No, because that doesn't start with 0 because it's empty. Good? I love to see what people mesh with this and what people are like. I teach, this is one of those things that I teach them like, yep, sounds good. Sweet. Okay. We are going to write 5 strings that are generated by this regular expression, A star B, A or B star. Ooh, no, why? Why not the null one? It has to have a B. Why? Yeah, so the concatenation ones, you can have none there. That's fine. But the B that's just sitting there in the middle, it does have to appear.
I was thinking that was like multiple.
Yeah. So B is okay. There's 1 string. Cool. What's another string that is accepted? A, B. A, P, A. B, A. Choosing none of the A star, choose the B, obviously, and then choose A. Right? Okay. B. Yes. Sorry, I wanted to write ABBA. Again, B. Yes. Sorry, we did 6. Okay. Can we describe that in words? Could you come up with a string of A's and B's that we couldn't do? Just A, right? Any other string of A's and B's we can fit. But a string of just A's won't work. Okay. Because it's any string of A's and B's as long as you have a B that appears somewhere. My freaking iPad. Any of you have an iPad? Talk to me about this. Do you have an Apple Pencil for yours or no?
Yes.
You have what?
I have Samsung, I have no idea.
Oh, you have an Apple Pencil? Is it when your tip starts going bad that it is delayed, or is that a software problem? So what, should I update my iPad? Unfortunately, I don't have that capability. I'm not a what do we call these people who are in charge? I'm not an authorized,
Administrator.
rules. Rules, rules. Okay, are we ready to keep going?
Yes.
We're doing pretty good. Okay, sigma, our alphabet again is 0 and 1. We're going to find a regular expression that generates the language consisting of all strings of zeros and ones that have even length, oof, and in which the zeros and ones alternate. So give me some strings that would work. 0, 1.
This is even between twos.
It means like that's too long.
Gotcha.
Not TOO, TWO.
So 2, 4, 6.
Better way to say that.
But it's an even number of zeros to ones, correct? Just an even amount of characters in the string.
Even characters in the string.
Oh, so like 0, 0, 0, 1.
That would be fine, but it says the zeros and ones alternate, so that wouldn't be fine. Yes.
1, 0,
Okay.
1, 0, 1, 0.
0, 1, 0.
That's what I was thinking.
4?
You can't do 1, 0, 0, 1.
Alternate zeros and ones. How could you describe this?
Like in a symbolic, okay, you need like an or bar, and then 0, 1 with a little star, and then 1, 0 star.
That's it. Choose which way you want them to go, and then choose the number of them that you want. They got to alternate, so it's either 1, 0 or 0, 1 over and over again. Yeah. And that star being on each side means you're going to choose the side, and once you've chosen the side, you concatenate there, right? So the order of operations matters. If we could do the 0, 1 or 1, 0, oof, it's hard to tell which one's a bar. Like that you could do 0, 1, 1, 0. This would give you an even number of zeros and ones, which is what we were asking for, but it wouldn't force them to alternate zeros and ones. Does that make sense?
Right.
The difference there and where the star goes. Okay. How about this one? We want zeros and ones that don't contain two consecutive ones. So give me some strings that would be in here. I have no idea what y'all said. Okay, 0. 0, 1. 1, 0, 1. 0, 0, 1, 0. 1. 1, 0. 1, 0, 0. 1, 0, 1, 0.
0, 0, 0, 1.
I want you to give me some symbols now. I don't want to keep doing this. Yeah, like this.
Oh, sorry.
No, you're fine. It was just that last one was too much for me. I was good before that one. Yes, Brian.
0,
0,
star,
star,
or 0, 1, star. The only problem is you can't start with a 1.
Correct.
With the one.
This one you also, okay, if we do 1, 0.
I guess that then we both get big parentheses, put one in that.
Yeah, I was gonna just have
A big parenthesis and a 1 out here.
Yeah.
What if
So,
we put this star out here? Then we get to choose if it's a bunch of zeros. We can mix these, right? Before we couldn't mix them. We would have 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, right? But now we can do 1, 0, 0. We can do 1, 0, 0, 0, 0. We can do 0, 0, 1, 0. Can't do 1 by itself. That's a problem. We also can't end in a 1. So what we're going to do is put another choice out here
yeah, sorry.
with a bar. This bar, you're going to choose 1 to end with. And we don't want to star this because we don't want to end in 2 1s. Yeah. And if we had done this as 0, 1, we couldn't do this on the end. We'd probably need to do this on this side. We're going to have the option to do the empty string tacked on or a 1 tacked on. The empty string tacked on allows us to end in a 0. The 1 tacked on allows us to end in a 1. So we can do like this one, we would do 0, 0, done. This one, we would do 1, 0, 0, right? This one, we would do 0, 0, 1. This one, we would do 0, 0, 0, 1. Yeah? This one, we would do 0, 0, 0, 1, 0. This one, we would do 1, 0, 1. Yeah? If you put a 1 out here, you force them to all end in 1. So you got to leave that choice there to not do that. So you could choose a 0 here, I guess. Or a 1.
I had the entire thing flipped, so I was thinking 0, 1, and then have the 1.
Yeah, this on the front, you could do that too. Yeah, because then you could start with a 1, because if you have these flipped, you couldn't unless you put 1 over there. Yeah. All right, we ready to do 12.2? 12.2 is more fun. You think that was fun? Did you say that? 0, 0, 0, 0, 0, 0. Okay, so finite state automata or steady state machines. These are things that function like machines. So a language recognition is an application of finite state machines. The machine accepts a string in the language. If it takes the string, then it does a thing that it's supposed to do. These machines are called finite state automata. A vending machine is an example of a finite state automata. It takes your input of pushing the thing that you want and takes it to somewhere, and then the output thing is your Skittles coming to you, right? Or like, you have a program, your user puts in they put in their, I don't know, name, and your program spits out, "Hi, Emily," or whatever, you have them put in a year, and your program tells them how many or what day Tuesday is on February 20th of that year, right? That didn't make any sense. What day of the week February 20th is that year? Tuesday and February 20th probably don't work. You got what I'm saying? Like your user puts something in, your program does something as a response, right? Probably not that example that I used. So we're going to talk through like what makes up a machine. This is our finite state automaton. M. I'd never heard that word before. I started teaching this class, so that's fun. So we have S is a set of finite states. A finite set of states. So you can think about this like a baseball player or something who starts at home plate, and then to get a home run, they have to run all the bases, right? So they go from one to the other. So it's going through each of those. Each base is a state, right? And from there, something happens, and they get to go to the next one. So the I is your inputs, a finite set of inputs. F is the function that gives the next step. S sub 0 is the starting state. And big F is the set of final states. Okay, so obviously we should look at one to understand what on earth we're talking about here, right? Let's. So this machine is given to us by this set of things, S, which is our set of states, I, which is our input values, big F, which is a set of final states, and the functions given to us in this table. I am going to draw a picture. Great, love it. So something that your textbook does is when it is a final state also, so the final states were given to us here in big F, it will put these like dots next to them in the table. I think that's a great idea. So every state is going to have these input values leaving it. Which sounds weird because they maybe should be going into it. But yeah. So what we're going to do is draw a picture. So we're going to draw circles. I hope you're good at circles. Our initial state is S0. This is where we start. We have an S1. I'm going to draw my 4 states right now. We have an S1. We have an S2. And we have an S3. I also know that S0 and S3 are final states, so a string can be accepted when it gets there. So S0 and S3 are final states. When you draw your pictures of these machines, of these finite state automata, you are going to put double circles around the final states to indicate that those are accepting states. That's where things can end. The other ones are trash states. If they go there and stay there, they're in the trash can. The strings. Like F, J, L, K, K, K in the English language, right, would go in the trash because it's not going to be accepted as an English word, even if my son wants it to be. Okay. So we're going to start at S0. We're going to follow this around. We're going to draw a diagram. So we have in S0, if we put in a 0, we stay in S0. So what that's going to look like is an arrow from S0 to itself that tells us what happens to the 0.
So what happens to the 0?
Yeah, so the input is 0, and this table tells us that when you put 0 into S0, it stays in S0. When we put 1 into S0, it goes to S1. So we're going to do an arrow from S0 to S1 that marks that that's what 1 does from S0. Once we are in S1, when we put 0 in, it goes back to S0. So we're going to go like this and put a 0 up there. It's going to go back to S0. If we put a 1 in to S1, it goes to S2. Are we okay? If I put a 0 into S2, sorry, then it goes back to S0. If I put a 1 into S2, it also goes back to S0. So I'm going to just put it on that same line so it can travel that path with the 0. And then going in S3 now, if I put a 0 into S3, it goes back to S2. If I put, oh no, I got to go all the way around my diagram here. If I put a 1 into S3, it goes back to S1. So I need to make sure that I have a 0 and a 1 coming out of every state. So here's my 0 and my 1 out of S0. Here's my 0 and my 1 out of S1. Here is my 0 and my 1 out of S2, my 0 and my 1 out of S3. What types of strings would be recognized in this example? That means that it takes a string of zeros and ones and takes them to a final state. Just 0. Actually, 0 star, right? Because you can just do 0, 0, 0, 0, 0 and stay there. One, 1, 1. So we would go 1, 1, 1, 1, 1, 1, 1, 1, 1, multiples of 3 ones. 1, 1, 0, star. 1, 1, 0, 1, 1, 0. 1, 0, 0 star. You got to get back first. So 1, 0, 0 star. You need that 0 there, Michael, because if it's just, oh, no, that'd be fine. Just 0 stars. No, not fine. Because, yeah, no, I was right the first time. Sorry. You do need that 0 to come back. If you do just 0 star, you could choose none. Right? The concatenation is any finite number of them, including none. So that would mean that just 1 would work, and that doesn't. So you need 1, 0, and then 0 star.
I mean, like, parentheses, 1, 0.
Okay, well.
That too. I was going to say that next time. But now isn't that one covered by the other? Oh, never mind.
I wrote this down, and y'all tell me if you think it's wrong, but I wrote down 0, 1, 0, 1, 1, 1, 1, 1, 0, star. And I think that, I mean, that hits this one too, because you would do this, and then this. It hits this one, obviously. It hits that one, obviously. It hits that one, obviously. It hits that one, obviously. I think, and you could combine any of them. It's interesting, maybe, that S3 is a waste of space. Nothing's going into S3, which means it, as a final state, is doing nothing. So that's like a programming situation that that you'll be looking for to make your program better, more efficient. Is that state is useless. And so getting rid of it altogether means less memory, less time, less everything, and better for your program. Yeah? Look at me. Does it sound like I know what I'm talking about? Yeah, no, this doesn't look like yours anymore.
I think I might have changed.
I sure did. Do you remember what I said earlier about machines not accepting strings that don't fit the language? It's like I was just hoping for a teaching moment. And we have it, and it's fine.
You need demonstration.
We will start this on Monday.
When I showed up to this class, I didn't expect to get my coding PhD here too.
Well, sorry. Sorry about that.
So you just type everything out with that,
Some of it, yeah. But it's got to have it's got to know what program to use to do it. So you got to call the package, and I had forgotten to, yes. But that's why I didn't type another one on your homework. I asked Google AI to do it, and it didn't do all the things right, and I couldn't make it. So I know, it's a bummer. Y'all have a good day. I'll see you on Monday. Have a good weekend.
That sounds like the extent of my programming ability.
Are these yours?
Yeah.
Okay. You're gonna take them?
No.
Why?
Already, you gave me 2.
Oh, so they're not yours anymore.
Yeah, they were mine.
Okay. Oh, thank you. Sorry. Y'all got this. Yeah. Hope you've eaten something. I know. You want me to go make you a cup of coffee?
I think I'll probably